Okay, let's get into general settings. Okay, let's get to general settings, which is nothing but the wizard of this particular tab. Assuming we are following that. Okay, again is annual flow analysis. We are adding cavities without flow conditions. Understood what this means yesterday. We are selecting heat conduction in solid. So obvious setup, heat is very important, and that's what we want to simulate. We are activating it. All our options are left blank. There is A has been used here. Though remains laminar and turbulent. We do not know what exactly it could be, or it can both. No high Mach numbers, no humidity present. Okay. Obviously, whenever we discuss about solids, we define the material for that solid. Now, in this wizard or in this general setting, we specify a certain material which can be used as the global material. In the sense, what material we apply here is applied to all the components of this particular setup. However, thereon we can go to separately and apply a different material. That is permitted once the solid materials tab over here once the thermal analysis is active. The way it works is, or the way we want to do it is, a material which is present in maximum number of components, that material you can use over here, and for the rest of the components you can manually give the different materials over there. Nothing much. Adiabatic wall, no heat. We are not simulating the heat dissipate to the atmosphere through the walls. U is not given. At the level, the temperature change in any of these parameters. It is all the same. Okay. So this is what it goes on. Quickly, the important things which you do even at the global level is initial mesh. So you can here we are left it at 3 and that's it. No much difference over there. So this could be the settings that one does in the wizard, which we saw through that. Typically, once you do that, it should show you. Oh, it is showing it. But let me try to show you this. So it should create this particular closed domain. Show you the boundaries of the internal domain. We may not go in detail, but we are actually creating these lids as well before we start this analysis. So these can be created using the lids option in Flow, or they can be created in solid CAD separately. So all lids have been created in this simplified configuration. Anyway, even this can be seen as a process in the company wherein there is a configuration for a detailed design, and thereon there is one more configuration which is created for. So this, for any one geometry, a company or a group can follow this process wherein they have two configurations. One is more for designing and details. The second is more for simulation. Let me get back. So next, as I told you, the materials. So I use this thing, insert solid materials. Okay. It also be importing the data from model. So if necessary, we can import the data from SolidWorks model. It over here, which I should not have done it. But if the data are given in CAD, then even those can be imported automatically over here. And take one at a time. You can see here. By the way, importing material from CAD was a kind of new feature which was added around 2 to 3 versions back. It is very useful option. Even there are many components, even as more than components, then it is a difficult task to remember and apply those solid materials from simulation one by one. Instead, when import it from CAD, of course, thereon we can explore it, understand if it has done all good. There could be materials which are custom up in CAD, those not be detected. So all those changes can be done. However, at the global level or at a generic level, there is this option, and you can actually import material from SolidWorks CAD to FlowSimulation. Okay, this is what it comes. So here they come. If I take them and just have a look at it, so components, these two resistor capacitors have been done the material of copper. Now highlight. Typically, if I take the design of a capacitor or a resistor, something like that, it actually has many components inside it. Like it may not be as simple as a solid geometry. So unfortunately, we are not simulating it in complete detail. We are external geometric details of that one, and we are giving the appropriate heat generation rate to the setup. Okay, this is what happens. So please be aware of this topic, and it's okay to do that because electronics has many complexities, and we are not simulating all of them in detail. Just the way we discussed for fan model, for the chip model or the capacitor model as well. If company is into designing of capacitors, then they might want to do a detailed, thorough, localized analysis of that capacitor, the different chapter, and they can of course do it. The process, but here we are looking at a more broader level of electronic enclosure, and these minor entities can be neglected. So this I just go on applying the material for different components over here. One of the interesting things would be PCB layer. Okay, so this module we are using a simple anisotropic material for PCB layers. But if electronic cooling system, they can actually give the details of all the layers of the PCBs and amount of copper or the silver tint into that. Okay, but here it would be simple single solid represented as a PCB. What else? Yeah, this is what it is. It goes on in this way. Now what remains is the areas from which we expect the air to come in. All the surfaces have been represented at an environmental pressure, the default environmental pressure. All these side faces you can see here, represented as environmental pressure condition. So they come in from here. Second, now this is a new thing which we'll be learning here today. So if you see here, the fan option, by the way, I have taken it from here. You can also get the option from where did it go? Okay, find it difficult to find here, but you don't know it is here. Insert a fan. Okay. Okay. Here. Sorry. So fan option, and we can go and edit it. Okay. So let me get into this. So any component which you think you want to represent as a fan, we have this option. There you can see we have three different fans. One is inlet fan. There is also an external outlet fan. There's also an internal fan. Okay. Oops, I wanted to do that. Okay. So as the word says, the one we are using now is an external inlet fan. Okay. If I zoom in down here, you can see here, this fan is going to help us blow in air into this system. So this interesting, try to understand, this is not a fan which is blowing out the air, but it is actually blowing air inside this system. Okay, inside this system. Saying that, I believe these two should be comfortable to understand. Apply to throw the air out of the system. Internal fan would anywhere inside this system. So I take any of the components inside here, which can or look like a, or we create a representative component for a fan, and that fan is going to create a turbulence inside the system wherever it is being represented. So that can happen using this internal fan option. Okay. So I have the external fan here. I select a face. So which is this particular face? It will doubt. So remember, almost all times that surfaces for boundary conditions or fans, etc., especially as an external or an internal or an external inlet or outlet fan, the face will be the face which is contact with both the solid and the liquid. So internal phase, there is no liquid interaction at that surface. Say it will be the internal phase. So that appropriately, the internal phase of this particular lid has been selected. Okay. Now in terms of fans, now it is a bit of confusion for me, but in the sense, all that you are seeing here may not be available if the customer is having only flow simulation. Remember, most of you, even while doing a demo, you might see all these fans, but do not be available for all the customers. There are some easy separation here, but this is the fact at the moment. Local fans are available for a license of flow simulation. However, with electronic cooling system, we actually get a more comprehensive database of fans. Okay. Now, I assume and I believe that this particular fan is present in flow simulation itself, so that's fine. So I click create, and this is the engineer database that we were discussing. This can be accessed from a different feature as well, but at the moment we came here through fans. Okay, and the fan that has been selected is this one, which is a axial fan. Is 400 and 405 has been selected. Okay, important name is fine, comments no big deal, fan type, fan curve. Okay, these are all excuse me. Now most important would be this one, the table and the curve that we are giving here, or which is present in the software. So this is the most important curve that you might want to understand for fans. If you're not comfortable with it, please try to explore in more detail what exactly it means. Best to explain it over here, but this needs to be understood well. Okay. First of all, okay, at different at different pressure difference. So typically, depending on the pressure that it is coming or it is experiencing and of the inlets, okay, the fan will behave or deliver a certain amount of output. How is defined? Output defined by the amount of flow that can happen through the fan. I'll just clear my throat. Okay, some better. Okay, so now depending on the pressure that that particular location is experiencing, flow rate is decided. So I mean it is experiencing a pressure of around 20 pascals, then expect a flow rate of around 0.0014 from that particular location. Now it is a bit more complex than what I am saying here, but if it is to be put in simple words, this is what it is. Typically, fans are very efficient at a certain pressure in a certain way. Now, just some funny things about this curve. If you observe, difference of 0, okay, for pressure difference of 0, actually, I can expect, say, or let me recollect myself what I was trying to say. So for lower pressure, okay, not 0, let's talk about a bit lower pressure. A comparatively lower pressure drop or somewhere at the inlet, the flow rate is 0.00, probably 0027, okay, meter cube per second. So when the pressure is almost 0, the volume flow rate can go up. It appears to be going up, but other way around, this is a kind of flow that is happening purely because of the efficiency of the fan. So fans are throwing out the air. So it could be other way around also. The pressure is comparatively high. The pressure is comparatively high, but the fan blades themselves can create a resistance and flow may not be high. So it might appear if I have an higher inlet pressure, obviously I can expect a huge amount of flow to be happening, but that is not true. That may not happen, or it could be inefficient flow. So I'm not sure if I'm able to convey this point correctly, but a particular amount of pressure, the flow rate is set to be optimal. Is the efficiency of the fan is maximum when in the graph we are seeing only one graph. Typically there will be more graph which show the similar characteristics for the system. It is not for the fan but for the system. Graph, if I show you, it might look something like this. It goes like this. And there will be a point somewhere around here at which the fan is expected to work at the highest efficiency. At that particular pressure difference, the system, if it can exert or it is working, then the amount of flow rate can be maximum or appropriate, as well the fan is used to its complete efficiency. But that, assuming none of this discussion is relevant here, the important things that a fan manufacturer can give us is this particular fan curve, which is just, if you put it simply, it is giving us different pressure difference for the fan. What is the amount of flow rate that it can deliver? Okay, it's as simple as that. And it can be we need it to represent or simulate the fans without blades, without any other components, but just using a solid entity over there. That's it. These items. Okay, let me go. I thought there was some question which came in. Pressure in the back and front of the part of the fan. Here it is the pressure difference between back and front of the fan. So other way around, if I see here, where did it go? Anchor, volume, flow rate, setup, density, pressure, static pressure increase. What did I show you? Table. What is an external fan? It could be a little bit different. Let me check something for you. Let me go to an internal fan. Okay. And let me select create and edit. Let me run for you. For same. Okay, fine. I think your details here. Internal fan. This is fine. This is fine. This is fine. So by the way, you can the face that is selected, so that the coordinate system is selected appropriately, and the x direction is actually the axial direction of the fan. Okay, and that is done appropriately. Thereon, let me go down here. Yeah. So the external fan, I would say the outlet pressure can be seen as this one, and the inlet pressure is defined by the pressure that is coming in the system. Help us create the pressure difference for the setup. To answer your question, David, and this we discussed as well. The angular velocities, temperatures are fine. All other things okay. Anything need to discuss about fan? If I have missed out anything. Any questions, guys, on using the ready-made fan in the software? This is fine. Okay, fine. Let me. There's a nice image down here. With the fan curve, there will also be a curve for the system. How do we get this curve? So the curve for the system is not derived, not to be input to the software. It is the curve which you can imagine in fan. If I have to do a similar kind of curve for this entire system, that is this entire system. Okay. It is called as the system resistance, and that curve is what I was trying to explain when I was drawing that particular disk. So it need not be input. In this case, that particular curve is derived or automatically assumed based on the loads and boundary conditions. So that's how it goes. But around given a fan, it efficient at a certain pressure drop in this system. It may be at another pressure drop in one more system. So around depending on the resistance of the system, the fans are decided. And of course, one interesting fact, of course, for deriving this curve as well, one can use a software like FlowSimulation, but not only for fans, but also for system level curves, one can use a module like FlowSimulation. But really, the fan curves are discussed in more detail, and the system curves are not discussed, or around, if I put it, the system curves are not standardized. They depend on many factors and as the geometry. However, the curves are very localized and can be realized or can be um, replaced. If in terms of the train manual, the text they try to explain you is somewhere here, the fan curve. Uh, the point I mentioned here is something like this. Fan can usually be obtained from the manual, not this one. It's recommended to select your fan to operate on the right of this stall region to ensure stability. So this is what is very important. This is the way fans are decided and selected. So here that has been used is this stall region. Now we okay. Let me check the chat window. Okay, let me this. Let's back here to the fans. So with environmental pressure, external inlands. This is what we saw now. Now we discussed there are different components here, and all these are generating heat. So we can absolutely select them. Ensure that you are not selecting the surfaces, but the solid geometries. Like this mistake will not happen in FlowSimulation, but in Sim we end up doing this mistake. Typically, the heat generation rate will be at body level and set the solid geometry. And heat generation rate value can give one. It can also be volumetric heat generation rate or temperature can be maintained. Appropriately, so all the different components which are generating heat, we are different heat generation rates. Here, of course, the sink as well has been given a heat generation rate, but I would saying or it is difficult to that into this sink is actually flowing from the circuit and it is going to dissipate through that. Then we have these capacitors for which a constant temperature has been given directly. So in one way or the other, if you observe, or I personally see this setup, it not be set to absolutely how can I say a practical example or a true example. It is more towards showing you different options. So in places we are using heat generation rate, some places we are using temperature. The heat sink, we may be knowing the heat generation rate, but heat just dissipates through it. So heat coming to it through a heat pipe or a okay, circuit that is present on the PCB. So it depends on those factors. So anyhow, in this we do not have the circuit, we do not have a heat pipe, and the heat generation rate has been given. I believe should be a simple input. What remains, or what is a new thing that we learn in this chapter, is this particular thing. Apart from applying an environmental pressure to particular surface, we also represent this as a perforated plate. Okay. Again, the option is present somewhere here. Flow simulation, insert, perforated plates. So, when I lost perforated plates. Yeah, here, sorry. It is somewhere here. And then once you go in that option, typically what I'm doing is I'm selecting the inlet. So remember, you have given the same surface as the environmental pressure. The same surface is selected here. There is, I think, these three different kind of perforated plates are there. If not them, you can of course create your own thing, use and perforated plate. And the details that are required are something like this. So one is name, that's fine, comments, hole shape. Now this is important. For the perforated plate, we have these many different kind of holes that you can expect. It could be round, rectangular, polycomplex, etc. So we decide what kind of hole it is, specifying the diameter of those particular holes, the diameter of the hole, and then the coverage. Check out distance, or I think I'll show it through an image. I'll explain it. Between center of those holes, I believe it is explanatory, and free area ratio, that is amount of area which is free or where there are holes to the total amount of area, that is this particular ratio. I think this panel has a good image on this. Yeah, something like this. I believe one is the center distance. So this explains everything. Image down here. No, checkered distance is fine. Okay. Area ratio, first of all, we'll see that one is the area of voids divided by area of solid. So as I told you, amount of area exposed or free for air to move divided by the total divided by the area of the solid, wherein there is no air flowing through. Calculated manually. Any use for explaining? It should be simple. Now, one important thing which I would like to highlight about the particular topic is again not simulating the holes as it is. So it is a perforated plate with all the details, but in summary, the software may not be knowing, or the holes may not be at the exact location as that in the actual model. As we may not expect the to be happening only from those holes. So these are not actuals, but these are imaginary holes. We are using this option only to create a kind of resistance which a perforated plate can bring into the system. Both resistance as well as amount of air that is permitted to come in through this particular perforated plate. In this case, the fan is blowing, probably the air is flowing out through this perforated plate. Okay, so actually I have two options. One is the perforated plate and one is the porous media, which we'll discuss later. For all practical purposes, theoretically, it is permitted to do so in certain cases. Obviously, if there are huge number of holes, we cannot simulate all the holes, and perforated plate is a for option to use. Saying that, remember, in simple words, what it is creating is a simple pressure drop or resistance to flow. That's it, nothing much. So not be able to imagine the exact flow happening through those holes, or realize it, or you create a flow trajectory and flow happening only through those holes. Those may not be visible to the eyes, but it is created appropriately. So this is what it is. In terms of goals, there, as we discussed yesterday, of course, all other goals are converged, but the goals which are most important or which you want to monitor here probably could be these two. So there is a chip which again is generating the heat, is supposed to be maintained at a certain temperature. It goes above, so I don't want to let it go above that and have it working efficiently. And there is a heat sink which is dissipating the heat from the system. So only these two probably are the ones which I want to monitor, understand, and do accurate analysis. So I get accurate values. So kept them as goals. It doesn't mean that other goals are not converged. All are converged, and oh, I thought let me all other things are also done. I have the results. Okay, I have it. Okay, while I load this, I felt I saw some. Didn't I load it? Mm-hmm. I don't mind, but I think it will take more time than I want to do. Let me check again. Don't save. Don't save. Let me go back. Finish. I've taken lesson 2. Okay, I've taken this example. Does not solve, then there is no option but to solve it again. Load. Yes, there. Let me plot one of these. Okay. Let me check the question that has come up. Okay. Okay. In this example, is a model to represent the heat sink. Yes. Can the heat sink be simplified using the heat sink simulation feature? Yeah, heat sink can be simplified using the heat sink simulation feature. But the feature that is present in the software in terms of heat sink is a more advanced heat sink than what you will see this one. Wherein you see here, these heat sinks, these advanced heat sinks, also have a fan in them. Okay, they are more advanced. They have a fan which works or sits inside these heat sinks somewhere at the bottom. They are all rather the fan sits at the top. Then there is a system which looks like the one in this geometry to dissipate the heat, and a certain surface which is connected to the solid geometry. So maybe the right option over here, sorry, not the right option, but depends on the application. There are heat sinks which you want to simulate, nothing wrong, you can do it. So there are also, I would say, scenarios wherein if I put it in a different way, there will be a chip which is producing the heat. Right above the chip, there is a heat sink which sits, and above the heat sink, a fan is sitting. There is an entire package that is sitting at a certain location, and the package works, or that system works. Now, instead of creating all these three, that is the chip, the fan, the heat sink, it is can be represented in a square block or a few two different blocks, and those that kind of setup can be created or used in heat sink. So, plain question. So heat sink with a fan on the top, you could simplify it with a block. Yes, you are right. You are right. Let's do this question result. Oops. Let me standard view. You see this? Okay. First of all, because of the flow that is being coming in here, I think it should be interesting to see how it comes in. Oops, it's selected, and we'll have it in the form of velocity. Okay, and let's reset this particular domain. Wow. For obvious reasons. I would not like to comment why this setup is there in this way, but obvious reasons, if you observe this good setup, right? Sorry, I mean, this is a good design. No mere good design. Since we have holes all around here, if you observe this closely, actually the coming in from here, air is coming in from here, and it is just going out probably something like this, most of the air. Where heat is getting generated somewhere down here, right? With the probably capacitors as well, these are comparatively big, and is actually dissipated from this particular heat sink, and we are not taking it out of the system. So obviously, we can also be seen as an example to improve your design. What I want to do is prefer having fan somewhere here or, uh, or probably here. I think more better it can also be here, right? It can directly blow the air on the heat sink. But the problem is, if you blow the air on the heat sink, the air can get heated, and heated air can go all around the system, which is also meaningless. So better as soon as the air takes the as soon as the air takes the heat, it should go out of the system. And I believe a flow in this direction would be more efficient than anything else. So actually, I want, if I assuming that I cannot create any fans here because of the design requirements, probably whether I relocate this heat sink over here, maybe I have restraint and I cannot create holes here. I can relocate the heat sink internally somewhere on this side and utilize it. Or even this location would be perfect, wherein it blows in and it takes the air out. All this area is there. Definitely, this gives an idea on what I can understand and how I can play with the setup to improve the design. Let's go back to the cut plot, how it looks. Okay, let me say this. Of temperature is important for me. Let me plot the temperatures. Reset it to the minimal, and let me have the probe. Okay, let's see. So you can see the chip is somewhere at around 43 degrees and heat at 56 degrees. So this is how it is. Obviously, I want probably I want to reduce the or other way around. If I achieved the temperatures, then it's fine. If not, I want to reduce it. One more probably just a thought which came while seeing this. I also do something by which the air is not going out and it is deflected in this direction. It comes here, and there is a kind of recirculation which happens and takes the air out from here. So probably change the design such that it goes on in that way. So there can be many different thoughts, but this tells you how you can understand and manipulate and play with the scenarios. It is almost 1 hour into the session today. We missed lesson number 3, which is on thermal and on electronic cooling. I'm just scrolling through the training manual to check if I have missed out on anything, any important topics to be discussed. If you have any questions, please ask. There is one example in the exercise 5. You can later. Okay. So let's take a break. It is 10:02 now. Let's meet again at 10:10. Okay. So I can see one question. Do we know what fan is actually operated in the right region? Okay, there are questions which I would like to finish before I go. Before the break, what are these 2 questions? Let me check. So for you could simplify to a block. Yes. Wong. Do we know that the fan is actually operated in the stall region in this case study? Yeah, good question. Can you know if the fan is operating at the right in this particular case study, whether it is operating? Typical word that is in the industry is something called as operating range. We are not using it in this training manual or even anywhere else, but the operating range. In this case, I think yes and no. In this case, it would be more of an experience-based judgment. We see the pressure drop that is coming up physically. I mean, an equation, a goal, or a actually just seeing the values of pressure at the inlet and outlet present, that can give me a idea on what is the pressure difference that is present. Okay, then like this. Assume that I don't have this fan. Okay, get rid of this fan. I only have an inlet, uh, not really environmental pressure. Assuming I have a pressure drop from the inlet to outlet, and I create either a volume flow rate, or I want to see the pressure at that particular pressure drop. What is the amount of volume flow rate that comes? Or one simple experiment could be, I get rid of this fan. Okay, I don't have this fan. Apply a X or a, if I in values, I apply a pressure of 10 units over here. Apply a pressure of 8 units over here. Okay, so I have pressure drop of 2. Pressure difference of 2, I can find out what is the volume flow rate in these few different iterations to develop a pressure to flow rate curve, and their curve can be matched with fan curve to understand whether I'm running the fan at the right operating range. So that I can understand details, and other way around I can use this curve to decide which particular fan to be selected for this particular system. So I can say other way around, I can use this to find out the system level operating range curve. Okay. Unfortunately, there is no much theory on this topic in the textbook, but you always go online. You can search for topics like how to decide a fan, operating range for a fan, or system level curves for a flow. Should be able to get enough text on that topic. I'm not put it rightly or I explained it rightly, but there are ways to do it. When using, do we know what the fan is actually know what fan is actually operated in the right stall region in this case study? So just a quick one, continuation to my explanation. Of just seeing the results, we cannot tell whether the fan is operating in the range. In this kind of simulation, we are only capable or only understanding that location of the fan is good enough when dissipating enough heat. Okay. In terms of understanding the operating region of the fan for the system, I think we need to do a bit more analysis than what we have done. Must be the diameter of the opening represent the size of the fan used. Yes, ideally ensure that the diameter that is over there should match with the diameter of the data fan of the fuse from the database. Works even if it is not matching, but it does not make sense. Okay, be conscious about that. Good question. Pressure and flow rate at fan inlet give implications on the stall region. Is the pressure and flow rate at fan inlet give implications on the stall region? Yeah. So if it is other than the fan curve is the property of a fan. Okay, it is nowhere related to the system. So the stall region for fan can be derived irrespective of the system. When pressure difference that is coming from this system is completely different topic. But if you're talking about the fan curve, yes, it does specify, it does imply the stall region, or it can help us understand the stall region. Use heat sink simulation. I mean the setup. I don't mind doing that. Let me check if the training manual has it, or I get an example on heat sink and I'll show you. If not now, but in due course of time, in the next 1.5 days. Okay. Any other questions? Okay, a bit of silence. I'm not sure if I could answer your questions. Any feedback, guys? Is that okay? Have you got the answers for your questions? Break of 10 minutes. And my watch is around 10:08. We were at 10, 15. As you get free to pop questions through the chat window, I can discuss once I'm back. Thanks. Questions on thermal analysis before I close this setup? Okay, start. I don't see any questions. Good. Uh, I Let's go to lesson 4. Let me open the study. This sample where we are going into external flow analysis. Okay, how to define an external flow analysis, and as well we are also going into the time domain. So this analysis would include defects, and we are seeing behavior of this part with time. Uh, did I finish the setup so that I did not waste time solving? Okay, and for results in this, that's fine. Frankly, this is a very simple, straightforward setup, but the difficulty is in terms of solving. Okay, in terms of setup, these are in the wizard. In terms of selection, we are selecting external analysis. No much complexities involved, so these two checkboxes of excluding keys and internal spaces are neglected. Okay, fluid is water. It is a water has been selected. Liquid conditions default, and only difference that comes up is this one. So here the input, okay, the boundary condition or the way the flow is happening is represented using the global parameter of velocity. We are applying a global velocity in the positive direction. Okay, and the dependency option is used, and actually using an equation over here to apply this particular input. Let's see what this equation is all about. Let me get it in the. This is basically using the Reynolds number. We are driving the flow in appropriately. So let's see how it looks. Let me open it in the training manual so that I can explain your equation. So okay, I think I discussed about this equation in detail. I have to go through the other goals because we are actually using the drag force that has been calculated here, as well as the Reynolds number that we want to use in particular. So basically, if I put it in one way, Reynolds number is the one which can decide or which can be understood if there would be turbulence or not. Okay. And there will be many cases wherein people speak in the form of Reynolds number. That is, say the flow is happening at such and such a value Reynolds number, and that obviously can go down to basically a value of velocity. It will be translated into velocity. The Reynolds number equation is given in the training manual. If you are curious, then you can just check this. It's some here. Rho, it is t. Okay, the density multiplied by the velocity. As I told you, velocity would be derived here. L is the characteristic length and the dynamic velocity of the fluid. So you can see viscosity and density are from the material properties. Reynolds number, as I told you, either can see it as an input instead of thinking about velocity. One must also speak Reynolds number. So assuming you know the Reynolds number, rho and density are known, so we multiply over there. We can derive the value of velocity. Now L is the characteristic length, and I would say it is a difficult topic to discuss in the sense it depends more on our judgment, or there is no specification for that. We have to decide on what would be the appropriate length. Now one is the Reynolds number. Second, in case of the way it is seen here is when the Reynolds number is between 4 to 60. Okay, 4 to 60, we can expect, that is nothing but, now you can translate it into velocities. When it is between these things, we expect flow cylinder to be something like this or symmetric. So tip might come, it could be a nice vortex, and it just goes on, and it can also lead into a steady state flow. That is, it will reach constant, how can I say, constant flow. However, when it moves above 60, okay, when it moves above 60 to 100 on such cylindrical entities, it leads to a phenomenon called as von Karman vortex. Now, in this case, what happens is there is an imbalance in these two vortices, and the one comes from below can be something like this, can be a bit different. And it's just an imaginary thing. Please try to understand how it might be happening. And it does not only happen like this, but it will oscillate. So such top will become smaller and bottom, and this oscillates over a period of time. So it will remain constant throughout. And in this particular example, we are trying to play or create a Reynolds number which is more than 60. In this case, we are using 140 over here, and that Reynolds that velocity flow should create, or we expect a flow to be happening something like this, or what the von Karman vertex phenomenon can be visualized in the software. On YouTube, you should be able to find a huge number of videos showing this phenomenon practically as well, and you can see how fluid oscillates in those scenarios. So this, let's go down here to give, like, in setup it appears, why do we need all these complex things of giving the velocity using equation? Frankly, this not be required. Okay, the way I'm giving it down all the way down here. Okay, this, it may not be so much complex. Okay, ultimately if you observe this, nothing but numbers. These are numbers. I directly calculate it from the calculator and put the value over there. But assuming, but around two things. Number one, this is of showing you how to give the dependency option, or to how to use it, how to give an equation in the software. Number two, it also giving you the flexibility. Now, assuming all other values are known, I get a copy of this setup. I will just change the Reynolds number from 140 to 60. I just changed the absolute value in this particular equation from 140 to probably less than 60, any value, and want to check the iteration. That's it. So it becomes easier using these equations. You can play with the parameter that you know or is comfortable to you. Of course, creating it in the software is a bit difficult thing. That's okay. Which we will be discussing is present here. I think first we'll cover the difficult things in this chapter, and we can go into the flow. It is no big deal. It is an easy analysis. Where is it? Turbulence intensity, transient analysis, and solution adaptive meshing is also discussed here. That's fine. Let's finish the curve thing first. I thought it was quite close. Here it is. Okay. An important thing which we are trying to understand here is the drag coefficient, or using the drag equation. So the force or the drag has this particular equation. Again, rho density, V is free stream velocity, which can come from a goal. A is the frontal area, the area that is being detected to on the fell side, and CD is the drag coefficient. Okay, different objects have different drag coefficients, so these could be seen as standard value. In a flow with different Reynolds number, and Reynolds number can also affect. So Reynolds number translate into velocity, and that's what is happening. Now, when seeing this value, we are seeing this value in the drag, and before also calculating the force. Okay, the force that is coming. Now it is very simple. Looking at the global force in the x direction. Okay, we are taking a goal because there is only one component. Remember, if there are more than one component, you want to do many more things, or select a surface and an object to find this force, but this is a global thing, so no big, rather it is a easier thing. I select a global goal of force in the x direction, and I understand that force. This force, I take it into the equation. So you can see that the force is taken as it is. Follow the equation that we discussed just now to find out the is it the CD? So why is it writing CD? Yeah, the Euler shape. Sorry. So Reynolds number again. Now it. I said a few things about the Reynolds number and the correlation with the velocity. So again, the velocity, the equation has been used in the form of input velocity, can also be translated here to be directly, so that when I do any changes, I just play with the value of Reynolds number. And if I put me, I can create multiple configurations. I change the values of these number, that is 140 to 50s or 120s or 130s. In these different iterations, I can proceed with the analysis. No other changes would be required. These equations can make our life easier. That's what is happening here. So if I put it simply, wherein there is a cylinder object, this object is subjected to a Reynolds number of 140. this effect of 140 is brought through equation has been used to the velocity, and that has been used at the global level for putting the velocity. Secondly, to understand the drag force, we are using the equation goal. We are finding the force in the x direction, and that particular force is used to find the coefficient of drag. That's it. Okay. So this is the example all about. In terms of application, that is what it is. In terms of specifics, we'll see a few more things in what we are doing here. Let me go to the general settings. Okay, general settings. So extra time dependent. After we understood this is fine, this is fine. Parameters. Okay. So one important thing, I think this is a default value as well, but we expect turbulence in this case, no doubt, and we are using a intensity of 1%. Now, turbulence is a very big topic, and to understand and explain this is quite an involved thing. But I would say this, but at the moment I would say blindly accept this value and use it. Okay. Length as well. That is, we expect the turbulence to be for this distance from wherever it starts. And yes, this is what it is. Let me check the initial mesh. Okay. So comparatively using a very high mesh. Okay. Obviously, if you want to capture the pattern of the one current vertex, then obviously we want accurate mesh. Saying that comparatively I'm using a big domain. Okay, comparatively I'm using a big domain, and the vertex is expected only in a certain area here, only small area here. So obviously I want to create a finer mesh somewhere here, which is almost impossible to do it manually or using the these curves available in the software. And for such cases, we have this option of assignment of the mesh, okay, which can be used at the global level. So trying to do that, you can see here at in the global domain, we are creating a refinement level of 2. We can also limit the maximum number of cells the software creates. So let's not go on finding that the number of ellipse is huge and items out of control. So we can create a cap on the maximum number of elements that are created. In terms of time, you can see here there is a physical time of 80 seconds has been given the analysis, and it has been activated at the global level. So go find refinement to okay. In terms of goals, all are satisfied, has been selected. Any important thing? Auto freezing, disabled strategy, savings. Okay, we are saying it is solving for 80 seconds, but it will do the iterations at every 4 seconds. Okay, so that can happen. If you save it for more, then it is going to take a lot of time. Up every this is fine, this is fine. Okay, one copy. I don't know whether this would come in any of the future chapters for your interest. Okay, there is what as freezing strategy, and in this case it is disabled. If you want the software to either periodically or permanently do it, so there could be cases, assuming in this domain itself. Now if I take this domain itself, and if I take this particular thing, I told you all turbulence may be happening here and the flow is happening in this region only. However, areas somewhere here, okay, the areas, these extreme areas may not experience any variation of flow. So in case of transient analysis, I may not want to continue solving for these things for pressure and velocity. I freeze the flow over here. That is, it will calculate the pressure and velocity distributions, and we can reduce that much amount of calculation, and it can actually freeze it at that point. So that option has been given. Use cautiously where it is exposure option, but that can be different. Okay. Second, in terms of computational domain, the new different thing that has been done here is this one. We are selecting a 2D plane. That is, we are doing a 2D analysis here. This is not a 3D analysis. So I select a particular plane direction. In this case, it is XY plane, I give the details of the plane. I can see here we have the option of keeping it default or symmetric. So we can have symmetric analysis. I think in due course of time we have a chapter where we do symmetric. So that can also be implemented, and we can use this domain. The default is the 3D. We are using the 2D here, and we are setting a XY plane. And in this to represent it, we are giving certain minimal thickness to represent the normal directional flow. Be aware whenever we are doing 2D, the same logic that we discussed for simulation in terms of symmetry holds here. So do not expect, or we are assuming that there will not be any flow in Z direction. It would be always in the XY plane. It is going not to that, parallel to that rather, and normally there is no turbulence, there is steady flow, and it's almost zero. Okay, so that is a big assumption. That's what has been done here. Of transient with such a scenario can take a lot of time to solve, so we need to stick to that kind of setup. We solve this setup. It's expected to be a bit slow, but let's scroll to, or while solving this setup, let's any questions if at all you have it. I'll also solve through the training manual to check if any important topics I have missed out while speaking. Okay. Let me make this smaller. Okay. I thought the interesting thing could be velocity. Let me have a velocity plot here. Okay. Okay. Look. So it appears as though that number is lower, or it is a steady flow. Slow variations happening. Okay. Better than I expected. Yes, now you can see that. So this Karman vertex. Now this can thing, obviously it is doing many iterations, and let me check the goal plots as well. Okay. So the API, that's fine. So you can see it's going all the way till here. Okay. Now that you are seeing can forever, whenever flow happens on cylindrical object like this and at a high velocity. And the iterative analysis, that it is for 4-second thing, saving it, ensuring it is converged, one iteration starts. So the time dependent thing, and it continues. Let me questions are there. Okay, adaptive mesh decide where to refine. So it is as simple as wherever there is high level of turbulence, where is high level of velocity change, it improve the mesh. That's it. As simple as that. So if I relate with simulation, there it is the stress difference. Of stress, it will refine the mesh at that location. Here it is the velocity. Is the way the mesh will also look like a flow. That what you are seeing on the screen. We need to plot the mesh here. I forgot. No, I plot the mesh here. Okay. Any other question, guys? There's a question which says that can we do this setup on an aerofoil and expect accurate results? I think I know from where we are coming with this question. In fact, that such kind of turbulence modeling needs different kind of turbulence models. And as we discussed yesterday, we have only two models, that is K epsilon and the density model. So there are arguments on the fact that we cannot handle or give accurate results for certain kind of profiles, okay, especially that of an aerofoil, which is far more intricate, and we need to design it accurately. So I would refrain from saying that yes we can do or yes no cannot do, but as I said yesterday, most of the models, that is at least what I heard of, 80% of the commercially used profiles can be handled using the K epsilon model. But saying that, I also know that there are few more specialized turbulence models which handle more intricate profiles. Rather, there are softwares which can actually do the simulation for those kind of aerofoils. In terms of boundary layer, let's say the laminar flow layer, how many cells would you recommend to fill the thickness of the laminar layer? Now, typically they say 2 to 3 layers are required to be meshed or created in along the laminae. Especially, I'm not sure if you use plastics, it talks a lot about laminar flow, and it is gives options to capture those flows accurately. But depends on us. I'm using this kind of turbulence, adaptive meshing, as well as I forgot, but there are some options in the mesh controls which allow us to tell the software to create more number of elements near lamina or near the boundary layers. It can help us create the sure that the boundary layer is captured properly. But saying that, remember, capturing the boundary layer is important, especially if the component is very, very small and we are studying a small amount of fluid area. But once the fluid area becomes big, the boundary layer may not be of too much significance. It is fine to neglect. However, user is interested or wants to study the boundary layer, then obviously we want to simulate it accurately, create appropriate mesh, and then we can go. As well, in plastics we use something called as prism elements around there, and they are supposed to be better for capturing the boundary layer, and that works. Guys, this should be quick, but it is at solving. That's fine. I think I do that. Yes. Let me go there. Lesson 5. Lesson 5. Okay. Now assembly. Okay. Open this. Okay. Can do that. Okay. Solves. I'm moving on to the next lesson. We'll come back to that setup again. By the feature of opening a file even when a flow simulation is running has been introduced in 2015. So usually use multiple CAD files while the flow is running. Now let's as usual go to this setup. The thing that we'll be learning in this chapter will be actually subdomains. Okay, subdomains using fluid subdomains. In terms of the wizard or the general settings, again an external flow analysis. Okay, they've done it as an external flow analysis. That is dissipated the atmosphere from that particular plate. Okay, so that's why it's an external flow to the atmosphere. There, gravity has also been simulated, so there is no wind or any such thing, but the heat is dissipated only because of weight difference of the air. So that topic comes up. Fluids, we are using air here. It is as well as a refrigerant has been used in the second subdomain, which is actually these pipes. Okay, the refrigerant flows through these pipes to either transfer the heat from some other domain, other component, and bring it over here for dissipation. So both these gases have been added here. There is also something called as the default fluid, so that has been selected as refrigerant here. Initial additions, it is all same, except one thing you can see here. If you expect density differences to be happening, or the flow happening because of height difference, that is, where the fluid is across a certain length or a height, there will be high amount of pressure that is coming inside the pipe, and that can be simulated using to ensure that it is simulated properly. You select this option of pressure potential. This will come only when the gravity option is selected. Turbulence in here, no solid parameters, initial temperature of solid, that's fine. Okay. Second is the meshing part of it. What are keeping it at the default of initial? We are specifying manually the minimum wall thicknesses. So you can see the thin components, okay, as well as the fluid is flowing through a small component. We want to ensure the mesh is captured properly over there. So those thicknesses or the diameters have been given here separately. So this is it. And most important thing, the way fluid subdomain works. Okay, let me first show you this. So first of all, as this is an external flow analysis, it looks something like this. A big domain is created which is acting as the external environment. Okay. Second, one more domain inside this pipe. Now, whichever it could be through which the flow is happening, we need to create leads. So there is a domain which is working kind of flow, internal flow is happening inside that. That is represented inside this pipe. So is something like this. Now I define fluid subdomain. I select it. I take pipe here. So the way it is defined, like the way the software detects fluid subdomain is, once it has a internal domain. Okay, once it has an internal domain, something like this. So what I want to say is, we can select any surface in this particular closed domain. Typically, it is good that select the inlets or the outlets. It will convert, if it is a closed entity, then it will treat it as a certain subdomain. And they have the option of selecting the kind of liquid that is present in that particular domain. Okay, in this case, it is refrigerant. That's what has been done. And what else is there? Parameter velocity is fine. So we are giving a temperature, a kind of initial temperature to be at around -5 degrees Celsius. So you can imagine a cool liquid is coming in over there, and that's what it is all about here. Now, important thing for this particular piping system, imagine you are having another internal flow system. For that, we are specifying the inlet flow rate. Okay, in mass flow rate that is coming in down here. Second one is the static pressure. So we know the inlet mass flow rate and the static pressure at which it is going out. So this is a -5 degrees Celsius. Let me check the inlet mass flow rate. It is minus. Typically, the liquid that is flowing or the refrigerant is flowing inside it at -5 degrees Celsius, and it's just around over there. There is a heat generation that is happening. Oops, what did I do? Generation is happening in the plate. Maybe there is some chip or some kind of system which is creating that heat, and unlike what I mentioned a few minutes back, the heat is dissipated through the refrigerant to the atmosphere, or is basically taken out of the system from here using piping system. This particular what it is, but if say this, on this surface, now in this case is selected on this surface, heat generated at 200 watts. Okay, this much amount of heat is getting generated over here. Now this heat can be dissipated to both the atmosphere around here, which is the exterior domain, and the air is present over there, as well to the liquid that is going to flow in over here. So this is how I would say how entire system is going to work. So what we might learn or we understand from this setup is how to create this setup. Okay, how do we create this setup? And for a multiple domain, that is, if there are multiple liquids, how do we handle them over here? Now, one important thing which I would like to highlight: typically, we all know the fact that flow simulation cannot handle phase change. That is, water turning into steam and other way around. So that we know it cannot handle. Saying that, we should also customers may not speak the same language, and they may just ask us, can you do multiple liquids? So it could be cases something like this, where I have multiple liquids flowing into different domains or different subdomains, and it's fine to have it that nothing wrong. And this kind of behavior can be simulated in the software. So customer is talking in that topic, please give a bit more detail and understand what exactly he means. Second, we can actually mix, say, liquids with liquids and gases with gases. So it is not, we cannot mix liquid and gases, but that is, we can mix gases and liquids with liquids. Please remember this fact. We can see how they mix. We can see what would be the concentration of these liquids at different locations or when they go out of this system. Finally, one more important thing in terms of mixing. Yeah, remember, whenever such mixing happens, there is chemical reaction and there may not be any thermal interaction as well. So it is more of flow and how it is going to mix and how it is going to go out, and that's it. Okay. Finally, in terms of absolute phase change, remember, we can handle phase change for steam. So if if the fluid is steam, then yes, we can handle it. And or the limitation or the way it is seen is up to a 50%. I'm sorry, whether it is the humidity or the amount of water. I forgot, but something like that. There is a small limitation over there in terms of steam. If it is steam, then you might want to use the software and understand in more detail on what we can do even in terms of phase change. Okay. Please keep these things in mind when you are concluding or accepting or going with it. Is running. I don't know if this result is there with me. Unfortunately, no. Let me test my machine with one more solution, whether it can handle it. Well, please ask questions. Is there an option to define initial condition in the subdomain? The subdomain had that option, right? Just now we saw it. It does have the option wherein we are giving the initial condition where we saw it was pressures and temperatures. So yes, it does have, and we can give it. So this is going here. Obviously, flashing, I cannot minimize it. What position of the machine? Do I have more power? And 4. Yes. Giving its limit. So I think, is it B? I can stop this. Do you want to see? Yes. Yes. Once there, let me read it. 2 more questions. Could FlowSimulation consider natural convection even if no specified. Couldn't automatically consider. First of all, there is nothing called as automatically considered. So it is not there. If yesterday I showed you the option of the wall boundary condition. So using the real wall boundary condition on the external walls, we can manually give a convection value over there. If it is not given, then it is treated as an adiabatic wall and no heat transfer happens. So that's that way it works. Okay. Is there a way that the software can stop calculating in trend analysis when it reaches the steady state and let us know the time required to achieve steady state without setting any particular goal? No, goal would be a must. So we can tell in the goal on when to stop. So it could be a case wherein I am monitoring a certain parameter inside the goal. And if you remember yesterday we had options to stop the solution. So one was one of the particular goal is reached, and it could be a case something like that, and that can be done. But in if I remember, one of the next chapters is more towards the time to reach a particular step. Okay. Now I think if I to put the answer in a different way, obviously the goal is required. I also want to plot goal versus the time plot, and when it comes flat, we know it is reached a steady state. But there it can stop automatically. There is only what we can control is through calculation control options. Those are the only options that we have in our hand to stop the solution. I think I stopped the other solution. Let's quick have a look at that one. Okay. Solution. Let me results. As a result, one interesting plot would be this case, that is the von Karman vertex. We never expect it to reach a steady state. Okay, that's why this particular scenario comes into picture. Taking so much time to plot the result. Then give it more time. That's fine. Okay, in this particular chapter, that is lesson 4, apart from this 2D analysis, transient, etc., one useful option which has been highlighted or explained is that of animation. Okay, if you go to page 131, that's what it shows over there. Yeah. So if this plot comes up fast, I'll try to show you that. Else, the nice thing, please go over this option in detail. It can create nice animations out of the results they're creating. Okay, this number 131, and that's where it is. My machine too much with two solutions going on. If plot is also decent enough, I can stop. Create actions and lead to action. 4 seconds. Let's see what it does. I need to stop it. Okay, I think this question is answered. This goes on. I think we have almost covered 2 hours today, so nothing wrong in giving a break. So, but I'll have a quick break. This is more to stop this thing and just get it going again. Um, it is over here. We'll start at 11:10. Okay, we'll start at 11:10, or at least 10 minutes is okay. So again, I'll start at 11:15. We'll restart at 11:15. Thank you. Yeah, Michael, just we are 11:15. I just gone through the model. Yeah, there are few attentive people. Thank you. Back, let's start again. I click off. By the way, I stopped the solution. Just highlight something. Those who are not aware, loading from a file, okay, load from a file, you'll observe that there will be a different FLD files. One of them will be something like this, one FLD. It will also tell you if you want to exactly understand what this is all about. So are the results from iteration 1 to 7. You might find other FLD. In this case, it is 0, so it is the beginning, so forget it. But I think when I uploaded it for the other model, it actually for the wrong FLD file, and that's why it is taking a more time than I expected. Well, the results are not as good as what I would have expected it to be. But now that it is plotted, let me quickly check what's wrong. No vector. This is what is taking the time and value. Yes, without vectors, it looks a bit more clean. And mesh, interesting. Let's see how the mesh looks. Yep. So you see, even this is not yet converged. This is halfway through. So obviously we stopped it. But you can see the place where it is doing the mesh. Okay, that is very clearly visible here, and the way the mesh is getting improved over a period of time. So one interesting topic which you might face is, do you have adaptive techniques in flow simulation? Answer is yes, and this is one of the best in industry. You can see how nicely it has been, smartly it is capturing the appropriate fluid domain. Okay, correctly. So this is what it is. In small, is there any other results which would be? Yeah, I would obviously like to see a animation of the flow without streamlines, without mesh, nothing. That is only this much. Let's see how it looks. Does it capture anything? The solution halfway through. No, I will not do that. The other thing which I would suggest is explore this option of animation. You go through this wizard, and just follow the steps through it. The training manual is also giving you the steps to do it. Yeah, I think we need to select proportional uniform distribution. Okay, finish. Let me see if this captures something to continue. Yes. I think there are very few frames, as well as the options that are selected may not be correct, but there is no much explanation on theory involved in this topic. Please feel to explore it in detail, especially if you are giving animations and that for a transient analysis. That option is very useful, this animation option. Please. In this chapter, we saw a few different things. Number one, how to use equations at different levels, how to do 2D analysis, the relevance of turbulence, the interesting field of adaptive meshing. So these few different topics or things we learned here. Any questions, please ask. But this is what this particular chapter is all about. Okay. I don't want to say this. Okay. I think Tora, I need to keep all the solutions executed so that we can discuss in a more faster way. So second one was this one. Again, I stopped this session halfway through. It's okay, but way around I also saw a few results. They look good. The even halfway through thing. So now is the temperature distribution. So the liquid is coming in at 5 degrees Celsius, minus 5 degrees Celsius. You can get heated all the way when it goes out. Okay, and actually it is taking away a huge amount of heat from this system. I remember someone asked me whether we can give initial conditions for the internal subdomain. So the values that we are giving here, okay, thermodynamic parameters minus 5 degree. So this particular, I would say it as an initial condition. Then we also have the boundary conditions for that domain. Okay, that's fine. So this is the way we give initial condition for a fluid subdomain. Then we at load animation. What is the difference in this case? I did not understand the question. The question is load results and scenario animation. Loaders and scenario animation. What is the difference in this case? I am not talking about animation options. I think you are talking about the previous option of animation. I think I'll discuss that topic a bit later, because more than animations, plotting results, these things are far more important. So I'll definitely discuss that topic, but at the moment let me finish this. Second plot is this one. If you see here, someone had a question. So now the heat over here is dissipated to the atmosphere, which can be seen in a blue color using convection. So heat is dissipated using the convection modes. Okay, all the heat is getting dissipated using convection, and most important, this is happening because of gravity. It's happening because we have selected the pressure potential option. Remember these two things. Okay, and obviously the heat dissipated to the atmosphere would be less than what the heat goes out from the system. It is supposed to be more efficient, because there a efficient refrigerant is being used. Certain amount of conduction is also happening, whereas to the atmosphere is more through natural convection, and that's what it is all about. So this is what we learned here. Number one, using subdomains. Number two, using splitting natural convection. Again, this is commercial, or the common name is conjugate heat transfer. Moving from a solid to a liquid or a fluid using natural convection here. And what else did we learn here? Using a refrigerant, using multiple liquids. So goals, yeah, pretty much that's it. So things that we discussed. So any other questions on fluid subdomain? Alex has answered his question on himself. That me. So guys, questions as of now in terms of these two chapters that we discussed, or before that? I'll give a minute's break. Please feel free to ask. Frankly, we covered many things. Obviously, as I told you, compared to yesterday where we went very slow in terms of understanding certain topics in more detail, I think now that you know the foundation, we can discuss the important concepts in each of these lessons. Conjugate transfer. So in the exercise, there is an exercise on heat exchanger in here that can be more on the mechanical front. Okay. One important thing, we have this chapter lesson 6, where it goes. Zooming. Okay. Frankly, I would like to skip this chapter. There is no theory content in this chapter, saying it is more of a process. Okay, it is a process on how to do EFT zooming. And if I had to quickly show you something or say anything about it, then if I take this image itself, okay. So it's similar to submodeling of relation. We can do the analysis for this entire setup in a coarse way, in a coarse analysis, and then on I want to refine only at this particular location and do a more detailed analysis. So this is called as EFT zooming. There are a few arguments on why it is called as EFT, but that's what it is about, and that is being done in this particular okay. But me personally, if I can share something, I have not seen any of the customers using this option effectively, saying that it is a bit complex. It is an easy option to follow to do it in the software, but it is a bit risky to do it in the sense we do not know where we are taking the right parameters to the local region. Okay, so use it cautiously. Nothing wrong in learning how to do it, but be aware of the pitfalls that could be there in this. So I'm skipping this particular lesson, but scroll through if there is any other important concept that is involved here and that I need to explain. So yeah, the lists are transferred using this option, which is called as transfer boundary conditions. So we get a smaller entity and we transfer the boundary conditions from the bigger entity to the small entity. What are transferred? Obviously, it would be pressures, velocities, temperatures, and those things, which are basic quantities for any flow simulation. Flow project typically should be same, so at least while transferring, so you can clone the project. It is easier. Cut plot, yeah, we are creating a cut plot. Compare, that's fine. You have to zoom in. Yeah, some comparison is done. Goal conversion. Okay, fine. So I told you I'm going to skip the lesson. That's and I think it should be okay. It is more of a process, and you should be able to do it. Okay. So I'm to lesson 7. Let me open it and also see at a question which appears to have come. Let me check that. What's wrong with this? Oops. Okay. Not you have to open the file. Okay. Don't save. First, let me go back here and open this file. Okay. Quick to explain, I'll come back, but a difficult topic to execute. Let's see. Direction for conduction of heat through solids only, will flow simulation give a different result from solid or simulation? Now, again, this is a huge discussion that has happened many times. One fact, flow simulation is using finite method, and simulation is using finite element. And okay, so obviously I do not expect the results to be one-on-one, but at a broad level, if we have this discussion, ideally the results should be quite near or they should match. Okay, but there's no point in arguing that they are 5% off or even 2% off, because it can be difference, because ultimately they are numerical techniques and the processes are very different. In the case of, this is an example where we are discussing porous media. Okay, and the example that is used is this particular what is it, the exhaust manifold with some filters around. So porous media will, one of the common applications could be filters, which are used for segregating pollutants. Okay, and here it is. So one flag bearer for any or most flow simulation is dummy component. So please get comfortable with it, the way simulation handles. We use dummy components at many different locations. Some being used for fans, being used for perforated plates, even heat sinks is going to use that. When you go to electronic cooling component, or there as well rotating components for rotating region, they are also using dummy components. They are present all over. Now coming to this example, we have two dummy components. Let me hide the computational domain. Okay, let me show you those two components first. One is somewhere, oops, that is outlet. Where is the housing? This, yeah. So these components, okay, these two are basically filters and have been represented using dummy components. Okay, these, as I told, by now you should be comfortable. We are actually hiding or using the component control. We are actually disabling those components. So what is this one? And here there is one more dummy component, rather somewhere in the front. I believe that is used for also measuring. So dummy components can also be used for measuring. Components can also be used for mesh control. So you see they have many different applications. You get these dummy components, make transparent or hide them using this in this front end, as well as disable them in the component control. Okay, so this is what it is all about. First of all, we have these components which are being represented for a porous media which is going to be working as a filter. Now, the logic or the discussion that I had for perforated plate remains here. So, porous media, apart from creating more a pressure resistance or a pressure difference, they must be doing the exact job of that a perforated or a porous media. In the sense, porous media may be filtering certain things, porous media may be affecting the flow directions. So that may not be happening. Of course, because of the pressure difference, the flow becomes more steady. It may, if there is any turbulence, it might go down and it becomes flows in a different way. But definitely there is certain amount of approximation that is involved, and idealized geometry is being used here. On a quick note, let's see the settings. Okay, the internal flow analysis. None of the options have been selected. We are here as the liquid, fluid, wall conditions default, no other settings. That's it. So that's it. Area added and internal flow analysis. And those leads have every condition. One of them is the inlet velocity. So probably the gases are coming down from there. Okay, meters per second, and the outlet is made the atmosphere, but the pressure is maintained at a static pressure of the atmospheric condition. Then this is the most or the new thing in this chapter is called as porous media. Again, the option is somewhere in here itself. Perfect place. Where did the porous media go? Is here. Okay, so that can be inserted. So what select is that particular dummy component. The dummy component is selected. It can be predefined. There are a few ready-made predefined porous media. Okay. This option, if you can see here, metal, fish filters, efficiency filters, and a few different company-oriented filters in 2015. So in 2015, we introduced a few filters which are commercially available with properties. Now, because this was a big challenge in the past to have the details of filters, and it was a challenge how to calculate all these details for the filter. And we introduced it in 2015. So this should be of great help. If any customer using filters, then please explore if we have those filters with us, then life would be easier. In this particular example, of course, we are using the customized one as per the training manual, and it comes up with certain parameters. Now, one of the biggest question that comes is from we find these parameters. Okay, and there are different ways. Now, one of these which has been discussed is in the knowledge base. If you don't have it, if you are aware of this article, please find and download it for us. I think even online help has been updated with this content. Okay, let me check anyways. Okay, like this. How to determine the medium coefficients by simulation. Please note down this article. This explains you how you want to find out the porous media details. And the I would say in the sense that we are actually using flow simulation itself to deal with those parameters. Okay, either now it is a commercially available one and it is available in our database, well and good, you can use. If not, you need to follow this particular article to drive those constants, and those constants have to be used in the software. There is no okay, the other way out would be to do practical testing with a similar scenario, and the way the data should be available for the other content that is available in the software. I search with porous media in the knowledge base, or you can note down the solution number, and you should be able to understand how to derive the parameters for porous media. Okay, closeness, here it is. So B, again there are certain parameters which I don't know. not have any specific definition for that, but basically constants which defining the porous media is going to create resistance. Okay, so in terms setup, that's it. Goals whichever you want to monitor, and here's the inlet total pressure, outlet total pressure. Now the new thing which you might learn here, which you think is okay, the text is mid total pressure, but the point which I want to highlight is you can actually have the component anywhere inside the system, suppress or hide them. However, we can use those components create goals. Okay, there could be certain location inside the model where you want to measure a certain value. Then you use this process of creating those indications and calculate the goals over there. Yeah, porous media goals, pipe drop, converter drop. So using this system, they are actually seeing the pressure drops more using the equation. Okay, the pressure drop is seen at two things. The one is between the net and before the fluid gets into the filter, and then there is also measured between this between the filters. Okay. If we see the results again, oh, I don't have the results here. I think, yeah, I don't have the results. I don't think I should be venturing into solving this example. That's fine. Any external results that would be seeing here? I don't think so. But just again, I reiterate, the flow trajectories that you will see here may not be absolutely same as that what may be happening practically, because we are not simulating the porous media as it is, we are simulating the properties, especially the pressure difference. Okay. Units break, please think any questions on porous media, ask. Which says that I need to include the effect of pressure drop when I enter and exit an equipment which inside my fluid domain. How can I do it? It is possible for me to simulate the equipment in detail. It is not porosity medium. Okay. So you want to just simulate the resistance to flow, but you don't want to use the porosity. How about perforated plate? Difficult. I assume you know the pressure drops, right? I believe you may be knowing the pressure drop only. Just thing. Can I create a dummy component and apply pressures at the two ends? Pressures. So I do have a few other questions. I think, Alex, I would like to discuss more on this topic, but I think my question would be like, is this obstructing the flow completely, or is this obstructing only at a certain an entity? So in this case, I know the pressure there. Can drop. Okay. Drop pressure is known, so it moves from domain to another domain. How about multiple domains? Resistance only. Certain. So what I mean is it realized components inside the domain, or is obstructing the entire flow? Just if we can use multiple domains. In the first domain, the flow happens. The resistance in the center, which is more direct pressure boundary condition, and then this flow on the same moves. Can boundary condition help? Only certain resistance. Okay. I think I get your question, but I think I need to think a bit more on this topic. Okay. I think we take it one on one. Listen, guys, next chapter is very important, and the lecture for today, rotary reference, one of the biggest applications of flow simulation. Jumping on to that, let's say it. Please, any questions on this topic? Okay, questions? One thing in 2015 training manual 195. Go a bit more, I think. Okay, so the level of fan was already there. This is the example which was present, but to encompass the new feature of sliding mesh, one more example has been added. Okay, and that is the same example which you have seen in most of the videos for feature. It is this particular example of the pump. Okay, like this. This example has been added in the 2015 training manual, and is using the second method of mixing planes or the sliding planes. Okay, we already discussed this topic yesterday, but I don't mind repeating. So previously we could handle flows wherein the flow would come absolutely tangent to either the side and it goes out in the axial direction of the impeller. Okay. Whereas now with this particular sliding mesh option, we can many more scenarios, and obviously it is a time dependent analysis, so time factor comes into picture here. Now let me quick back here. So okay, this is from lesson number 8. At the global level, if I talk, it is the internal analysis. So this is the first setup where you will learn on activating rotation. Okay, the rotation is activated. It is not a global thing. So we are using this local region averaging, which was present previously. This option for the first lesson. As discussed yesterday, this was the sliding option was introduced in the as I said, the sliding option can be used for all the examples, does not matter. Obviously the solution time is a bit more higher for the sliding option, as well time dependent analysis. Okay, so say transient and the kind of technology will make it slower or more time to solve, but actually can address many more scenarios than what it used to do before. Our averaging option has a few limitations. So if your setup fits into averaging, then nothing wrong. Please go ahead and use it. Coming to this setup, averaging has been used. Okay, let me check fluids. It is the AF. So things apart from the rotation option that has been selected. Mesh. Okay. Initial, you can see here we are taking local mesh. So typically for rotating region, the mesh is very important. All you have to capture the rotation accurately. Ensure that, or the simplest thing which I tell the user is local component that has been created to represent the rotating mesh. You can use the same component. To simulate the amount of or the quality of mesh that you want to create. Okay, so that can be done. And in this case, of course, we discuss these options in more detail, but it can also be used to do the mesh. Okay. Okay. What else? In this, the control plane method has been used to get good mesh in that particular thing. Okay. The only new thing that comes up over here, or the option that has been used, is the rotating region option. So insert it from here, rotating region. Okay. On inserting, it gives you an option to select the part, the dummy component, which is being used as the rotating component. So remember, we are looking at a relative motion or the relative, relative frame of reference, something like that. So here the fan is not moving, but actually the liquid around it is made to rotate in a certain direction. When it rotates, it's the same effect as that what is rotating, and there would be flow happening. And yeah, this is what it is. Speed is 200 radians per second, and complexity, or ensure that you are selecting the right direction for rotation. It is typically right hand rule. However, the green arrow is showing the way or direction in which the fan is going to rotate. So that is selected appropriately, and you can see it is already grayed out and disabled, but the component should be disabled. That's it. Environmental pressure. So here the domain is actually simulated as an external flow, but to make the computational domain small, we are actually using a cylinder to simulate the atmosphere around it. That cylinder is being created and maintained at an environmental pressure at internal flow. So the interesting example which can tell you if a certain condition has to be translated from an external flow to an internal flow, you can also use this approach. Here we are controlling, so instead of square, we are also using a cylindrical domain. That's fine to do. So hence how to do it. Frankly, no much things. What remains is the force that is coming on the blades that is being captured here. Obviously, is going to come in the Z direction where it is blowing the air. So we find out the forces. Obviously, might be interested in the torque as well. So to create that force or to create velocity of the wind at 200 radians per second when it rotates, how much torque would be required? So obviously this torque would come because of the resistance present in the air, and that can help us design or conclude on the capacity of the motor that has to be used to create that much amount of rotation. And fill the mesh. So apart from the global controls, you can see here we are also using local controls. We are selecting the part, the dummy component, and the other refinement sliders can be used appropriately. So in terms of setup, this is what it is all about. Fortunately, again, I don't have the results, so that's fine. Anything else that is more relevant here? We have created these arcs in here, or these sketches, more to be used for flow trajectories or to have nice visualization of the flow. Otherwise, there is nothing different. So new things or the different things, you activate the rotation region in the general settings for the wizard. Now ensure that you have refined mesh at appropriate location. If you are curious, you can just run a solution without refining the mesh, and later on you can see the difference when you use the mesh, how accurate it will be. To the end, I have seen it does not capture itself the rotation if the mesh is not good. Okay. Thing will be the rotating region. This is another new thing that comes up here. So create a component to represent the rotating region. There are a few this is the right word, but tools or rules of thumb which need to be used when creating the rotating region. Again, those are present in the knowledge base or online as well. You can explore them. But it's simply, number one, it should encompass the rotating component. So in this case, the blades, ensure it is encompassing that. If any component which is coming inside this rotating region, then you treat it as a real wall and make it as a stator. That is, it is not going to move. The option is somewhere here. Insert boundary condition, real wall. You can see here there is this option of stator. Select those appropriate bodies which are coming inside the domain, and you can treat them as a stator. That is, they are not moving. And there are at least 2 to 3 elements after the blade. So if the blade is ending at a certain location, simulation. Can I take a standard view? Or can I hide the domain? Yes, I can. So if you open here, the blade ends somewhere here, and we do have this gap. Okay, I'm not sure if it is. Yeah, that's the one. So this gap needs to be maintained to ensure that you capture it accurately, even though this gap may be overlapping with something that is static. Okay, it's not matter. Create rotating region axis symmetrical as that what is done in this example, and then any bodies which are coming inside, you can make them static, no issue. What an important thing that I need to highlight for a rotating local initial mesh. Yeah, of course, local initial mesh can be further used to refine the mesh at the local body. More than using the control plane, I would suggest using the local initial mesh option to refine the mesh locally. What else? This is what it is all about. On solving, we will be able to if a fan is to be there, how it is going to flow, we can visualize it. Obviously, flow trajectories would be interesting. One, because we discussed this topic in a detail today, deriving the fan curve from these kind of analysis. So, as the fan curve was more of a different pressure drop, what is the velocity or what is the volume flow rate that it can give. So a similar scenario can be created as that of a practical scenario, and it can be done in the software. Just ensure that when a practical testing of a fan happens, it is simulated under a certain system, that is the boundary conditions. In this case, it was a big cylinder. It could be anything else in the actual fan. In fact, that particular system is accurately. Okay. Second, typically there will be huge amount of electromechanical and mechanical losses come into picture when a practical testing is done. That is imbibed in the practical curve. So obviously the curve that you get from the software will not be one-on-one with that particular curve. So we can get the curve. It is the same flow as that what is happening practically, but few things may not be captured accurately, and hence that is the lag between what can happen in the practical and deriving the fan curve using the software. So just be of that. The discussion comes up with the customer, you can say yes, we can do it, but this is where we hit the limitations. If we are comfortable and if we are aware of those limitations, then definitely FlowSimulation can be used to derive the fan curve. Yes. I think there are a few questions. Let me quickly check those questions. Is it possible to see flow of magnetism? I don't understand this. As you are talking about electromagnetics, no, in FlowSimulation we cannot simulate electromagnetics. There is this product by name ElectWorks which does that. Can combine motion analysis and FlowSimulation of rotating region. So there are a few nice animations which we can combine in animations, but not in terms of simulation. Okay, so fortunately no, we cannot. But fixing plane with animation, it does simulate that kind of effect or visualization. This plane itself, if I get mixing plane, so general rotating. I thought this is the one. No, not this one. Let me close it. Don't save. I go here. I go back here. Blower fan assembly. There's an animation as well. Can I see it? Open with Windows Media Player. Okay, over here. Okay. Oops, it is quite. Forget it. So now, if I use the other option, okay, the other option which was introduced in 2015, 15 is what is called as sliding mesh. You can see a local sliding mesh. It can use no other things. I mean, in terms of setup, no other difference. You are selecting time dependent option here. Okay, this is time oriented because the blades are simulated at different locations. You can imagine that does not happen exactly like that, but that's the way it is. Are same. Okay. Okay, you can see a physical time of 0.2 seconds has been given. Obviously, this will be rotating at a very high speed. So, small time is given. We are seeing, and then one of the goals is satisfied. Any other important thing that is here? Refinement, solving, and solving time step manual. Okay, to capture the animation accurately, we are also ensuring the results are saved after every 0.2 seconds. Okay, so we have all those results, and we can understand how the anode look or how the flow is going to happen. Period. This is okay. Okay, cancel. Okay, region again it's the same, absolutely the same method, and see it is moving at 700 rpm. It's huge comparatively, not too huge also, but it's okay. Comparatively, many goals have been given to, and we are finding actually the efficiency of this pump. So the pump efficiency equation is given. Okay, so it's typically torque, pressure at inlet and outlet, the pressure drop, and all those things. Those given, and point here. General setting. Local mesh is obviously given. We want to ensure it is captured properly. I assume results. If I load on file, somewhere else. No, I don't have. Okay. I would do something because I don't want to skip on this one. I want to show the results, the way it works, what is happening. So I got the solution for today, and I will discuss the results tomorrow. Okay, tomorrow sessions I'll discuss this result in more detail. But saying that, if you see setup, there is nothing different. It is all the same process. Only difference is in the wizard or in the general settings, we are setting the sliding mesh option. That's it. And handle many more scenarios than previous option of averaging. Okay. So we have last 4 minutes for today. Any questions, please ask. Not, that's it for today. Thanks for attending. We'll catch up tomorrow at same time, that is 9 a.m. Singapore time. Okay. Thanks a lot for the patience. It is difficult to attend from there. I'll take any amount of questions that can come up now, and let's call it a day for today, and we'll catch up tomorrow. Okay. Thanks a lot for attending. See the questions. I noticed that the flow company is okay to understand. Okay, conduction of heat is done. I need to include the effect of pressure that we'll discuss. I noticed that the flow simulation solver will terminate abnormally when I use high mesh refinement. Is there a reason for that? I don't know. So the solver being terminated abnormally is typically what we call as solver crashes. Okay, and it may only obviously it would be file specific. It cannot be generic. Number two, it will be it not be only because of huge amount of mesh, but there could be something more. And one of the common things will be few results. Now the base results, if we take like the velocity, the pressure or the densities, they are going abruptly high or abruptly low. The solver thinks something is solver is not able to handle those scenarios. So difficult to say why you are facing that error. It could be many cases, and it could be file specific as well. So if can, I would obviously like to discuss one-on-one on that particular file. The setting region method take effect of the geometrical characteristics of the impeller. Of course, rotating region is meant for that. It is rather you are using rotating region to set and understand and design the geometrical details of the impellers, fans, blades, etc. Okay, so the geometrical characteristics are included, unlike that of a porous media or a perforated plate. So definitely that is the purpose of using it. We can see the sliding mesh moving. For instance, like plotting the mesh in different time interval, can the mixing mesh used to simulate moving objects other than rotating region? So definitely it cannot be used for any other object apart from rotating region. Okay, that is for sure. And in terms of moving, as I showed you in yesterday's animation, we can actually see these things. I'm not sure if you saw this. Is rotating component. Okay, so this way it looks. So you can see seeing the movement of the blade, rotating component. So this can actually happen, and we can see it using an animation. Is it possible to see the flow of magnet? No. Can combine motion analysis? No. And thank you. Okay, that's it. Other question, guys. One more minute, and we can call it a day. We can meet tomorrow again.